Hi everyone, my name is Thomas Kim. Today is November 17th, 2019. This is my 30th episode about linear algebra and the threading building blocks. In this episode, I will discuss C++ programming best practice through matrix addition. Matrix addition itself is pretty simple and straightforward, so there is nothing much to talk about matrix addition, but instead I will help you understand a few guidelines regarding C++ programming best practice. First, try to conform to C++ standard. If there are two or more libraries, one is C++ standard library and the others are not, then choose the C++ standard library. One of the primary reasons you have to prefer to C++ standard library is that your third-party library could defunct, may not exist after 10 or 20 years later. So always try to use C++ standard library. The second is try to understand the design philosophy of the C++ language architect or C++ standard committee. I will cover the second issue in some future sessions. Third, don't assume your parallel algorithm always runs faster than its sequential version. 4. Make your C++ code readable to you after 10 years later. 5. Exploit C++ language 100%, which enables you to better express your ideas. C++ language is composed of two parts: compile time constructs and runtime constructs. 6. Try to use high-level C++ language constructs instead of low-level features. This does not mean you should not read and understand low-level constructs. You do not need to code in assembler, but still you have to have some experience in assembler. In the same manner, you do not need to code using low-level C++ multithreading constructs, but still you need to understand some fundamentals of the C++ threading technology. I will post this script in the description section below. By the time you watch this video, you can scroll down and click this link to download the complete source code. Now, double-click this link to download the complete source code from our previous episode. If download is completed, show in folder, unzip, extract the file, right-click, rename, 30, matrix addition. Hit enter, copy the folder, paste it to your working directory. This is my working directory. Start Visual Studio Code, open the folder, right-click template, copy, click folder 30 matrix addition, paste, right-click, rename, addition. Hit enter, Ctrl V, void test matrix addition, copy the function name, paste it here using element t int using matrix t matrix aligned fast matrix element t size t low count. For example, 4 matrix t a low count B, row count. We declare the two matrix, matrix T, C, row count, D, row count, auto generator, CHR, random generator, element T, minus 10 plus 10. We create a random number generator that generates instances of type element T ranging from minus 10 to plus 10 inclusive. CHR means chronorandom, random fill, A, array, generator, CHR, random fill, B, array, generator, stream, A, and L. I copy again, B, then start command prompt, dir cd 30 matrix addition. We are using Clang compiler, SDD C++17 addition.cpp LTBB malloc, hit enter. CLS. So we created two matrix 4 by 4 with random number generators. Now we do addition. CHR stopwatch SW for size T I less than A rows plus I for size T J less than A columns plus J C I J A I J plus B I J. or canonical sequential stopwatch elapsed CHR microsecond CHR micro T gives us elapsed time in microsecond unit. Or it should be reference array A array or reference array B array or reference array D array for size T K less than array A size plus K array A K array B K array C K array DK or smarter sequential SW elapsed time chrono micro T we display stream, canonical, sequential, canonical, sequential, and smarter, sequential, smarter, sequential. I fixed stream, canonical over smarter, canonical, sequential over smarter, sequential. And there I will copy once again. I copied, pasted. We now go parallel or parallel addition. We capture all or K. Semicolon here. Don't forget semicolon. Scroll up. Namespace. Far. Talk play fun. Parallel. Scroll down. Far. For index. Size T. Array. A size. Parallel. Addition. Far. Pause parallel. Okay, it means we are pausing parallel algorithm. This is optional. Now this is smarter parallel. I will copy once again here. Smarter parallel. Copy. Paste. Copy. Smarter. Sequential. Smarter. Parallel. Copy. Paste. Now here I will create another array. E. Row count. I will put another thing. Array E. E. Then I will put it E. And I will copy this part. Cut. Paste it here. I made silly things here. Sorry. It should be D, A, B. This is E, A, B. Then we display matrix addition. Stream. D. C, D, E. C. C. And there. D, E. D, D, E, E. Now in the command prompt, CLS, we build again O CUEXE. CU means it is an optimized version. Please note that this is an optimized build. Control Enter. CLS, CU, matrix A, matrix B. This is sequential algorithm. we compute C using canonical sequential. So C 5 minus 2 minus 16, 11. We add together matrix A, B. This is 5, correct. Minus 8, 6, minus 2. C is correct. D. This is matrix D. We use optimized sequential. D is also the same. E. This is optimized parallel. Okay, the results are the same. E is optimized parallel. The computation is correct. Okay. Now we disable displaying part. Ctrl K, Ctrl C. And I will also disable this part. Ctrl K, Ctrl C. Now we increase element type to double. I will just say float. And the count 10 row, 10 columns. Then we build again. This is an optimized build. CLS, CU. So canonical, sequential, smart sequential, smart parallel. Smart sequential is 1.8 times faster than canonical sequential. So simply modifying this canonical sequential algorithm to optimized way is 1.8 times faster. This is optimized parallel. We turned it into parallel algorithm. It is 4.5 times faster. The units are in microsecond. Once again, the units are in microsecond. Now we turn it into optimized version O3 CO. CO means Clang optimized. Hit enter. CLS CO. Smart sequential is 0. I will change it to double and increase it into 10,000 row by row matrix. Let's try if it fills. CO. So smart sequential is 1.14 faster. Parallel smarter is still 1.17. Please understand that we are releasing optimized release build. So the lesson we have learned from this episode is that parallel algorithm is not faster. If we try once again, our canonical sequential, smart sequential, smart parallel, the ratio is 1.1. Our parallel algorithm is not any faster, slightly faster, so it's meaningless because we are releasing optimized release build. As I said in the introduction section of this video, don't assume your parallel algorithm always runs faster than its sequential version. And I also said make your C++ code readable to you after 10 years later. That means this algorithm is good enough. It is easier to understand. This is optimized, but it's meaningless. This is parallel. This is still meaningless. If you create your algorithm like this way, anybody can understand. If you make your algorithm like this, only you can understand. Others cannot understand. If you have to, you can implement your algorithm like this, but I would prefer this canonical sequential algorithm. I can understand it after 10 years later. In matrix operation, what governs the speed or the performance of our algorithm is not matrix scalar operation or matrix addition, but matrix multiplication. Multiplication algorithm dominates the performance of our matrix algorithm. So we have to exert all our efforts and energies to optimize matrix multiplication. But in case of matrix addition, we can just use canonical addition algorithm. We don't need to concern to optimize matrix addition. In case of matrix multiplication, first it forms loop, outer loop, one level of loop. Inside the parallel algorithm, this is second level of loop, and this is third level of loop. So, one level of loop, this is n time complexity. Here, another level of loop, n level of complexity, another level of loop, n time complexity. So for n by n matrix, one level of loop, two levels of loop, three levels of loop. For multiplication alone, n by n scalar multiplication. For n by n matrix, n by n additions. See, you see this addition, this multiplication, the same number of additions. In total, n by n multiplications plus n by n additions. It's a huge operation. Compared with multiplication, so we can say in case of matrix multiplication, 2 times n cube operations, including both multiplication and addition. If we compare addition and multiplication, the operation of multiplication is very huge. In computer science, when they say time complexity in big O notation, they usually drop constant terms. So in big O notation, they usually say big O n cube for matrix and matrix multiplication. If you refer to Wikipedia about matrix multiplication, its computational complexity is big O n cube for n by n matrix. I hope you understand big O notation actually does not reflect correct timing of your algorithm. It just gives you general ideas. I hope you understand what time complexity means in big O notation. It only gives you general idea. In my next episode, I will talk about exploit C++ language 100%, what it means. Please subscribe to my YouTube channel. Thank you for watching.